Good morning. We will continue our discussion on analog electronics, and today we will discuss about little bit about digital logic inverters. Okay. So, this is the symbol of the inverter. This is logic symbol. So, inverter logic symbol is this knot or bubble is used to show that the logic is inverted. Okay. So, what is the working principle? If you give a logic 0, you will get a logic 1, and if you give a logic 1, you will get a logic 0, right, it will invert. Now, what do you mean by logic 0? Logic 0 is nothing but ground connections or the minimum voltage available, and similarly this is, so one is VDD and another is ground or minus voltage, what is minimum supply. Okay. So, this is our logic. Now, this is a symbol, right. Now, if you want to look inside this, that what is the circuit connection. So, this is the circuit. Okay. This is one type of circuit, there could be different type of circuit. So, this circuit is resistive load CMOS inverter. Okay. This load is resistor. So, this is resistive load CMOS inverter. So, can you tell me this is which kind of circuit you have seen? This is like a common source. Okay. So, if we give a full swing, means like a digital square wave, this circuit will behave like a digital logic also. If I give a bias and then a small signal, this will behave like an CS amplifier, but if we give a full signal like a digital logic, then this can also behave like an inverter, that we have discussed in CS amplifier class also, right. So, generally we do not give full swing for amplifier, right, we have a DC point and we give a small signal, but for digital logic we have a full swing, matlab maximum possible swing, okay, 0 to VDD. All right. So, we know that this will be when input is 0, output will be 1, and when input is 1, close to VDD means 1, output will be 0. Okay. So, if we plot the VTC, VTC means voltage transfer characteristics, it will look like this. Okay. So, you see when input is less than VTH, what will be my MOS Q? In which region? Off region. And when my input VGS is very high and VDS is low, it will be in which region? Triode or linear region, right, and in between it is in saturation region, right. So, in this case this is behave like a digital, and in between this it is behave like an analog amplifier, right, we have seen this. So, this is our ideal VTC. Okay. Now, see this up to this my logic is output is 1. So, this much input I can consider as logic 0. See my input when it is 0, it is logically also 0, but when still it is rising up to little range, I can still call this as a logic 0 input. So, that is happening even if input is increasing, still up to this range or margin, this will be treated as 0. So, this is known as the noise margin low. I have a margin, okay. The voltage may not be 0, little bit above 0, but still up to a range it will be considered as 0. Clear? Similarly, at the high side you see, after when it is crossing VIH up to VDD, when this input is in this range, my output is 0. So, this is my margin for high side. So, this range my input will be treated as logic high. For example, suppose you have a 5 volt, 0 to 5 volt. So, 0 volt means your logic 0 and 5 volt mean your logic 1. Now, what is the middle point? Middle point is 2.5 volt, right. So, maybe say you can tell that 0 to say 1.8 volt is my, still it will be treated as 0, and something like say 3 to 5 volt will be treated as 1. So, this become my noise margin low, this become my noise margin high, clear. So, now how to define this VIL and VIH, V input low and V input high. So, when this VTC is falling, the point where the slope is -1, this point is termed as VIL, and when this VTC on the higher side is again going to flat, where the slope is -1, that is termed as VIH. Okay. So, how to define this, what is my input VIL low, that is this corner. Okay. In real plot it will not be that sharp, it will take a slope, and the where the slope is -1, that corner is my V input low. Similarly, on the higher side, when the input is on the higher side, output is falling, that time this corner is VIH. Okay. So, this is my margin. Margin means even if input is suppose fluctuating like this, still if it is less than VIL, it will be still be treated as 0. So, you can understand that digital logic circuit are more robust to noise, because I have a margin, this much margin noise it can absorb. Similarly, at the higher side, even if my input is falling from VDD, still up to this level it will be treated as logic 1, clear. So, this is the noise margin, this is the definition of noise margin, and this is the definition of VTC. Now, this circuit, so you see if this is off, as if this circuit is open, open from which terminal? Which terminal? Ground terminal. If this switch gets closed, what this output will be sorted to which value? 0. Now, this is open. So, I can't have 0 here. What I can have? If this is off, so no current flows. So, V0 will be logic 1, right. Similarly, if this is sorted, suppose this switch is close to sorted to ground, now what is my output? It is sorted to ground, na? So, logic 0. So, this CMOS is behaving like a switch, either off or on. Okay. So, we can in digital circuit we can replace the MOS with a switch and analyze the circuit. So, this circuit it is in the only it can pull down, right, pull down to 0. So, this is called pull down network. Whichever is at the lower side it is connected to ground. So, it is only pulling down the voltage to the 0. So, this is known as the pull down network. Okay. Now, let us discuss again. Suppose my Vi is 0, MOS will be on or off, it will not get VTH, it will be off. So, switch is open, switch is open means it is disconnected from 0 and no current flows. So, this will go to VDD means logic 1. So, my input is 0, output is 1. On the contrary, suppose input is very high, VDD or logic 1. So, this switch is now closed, it will have a very small resistance, that is R on, and a large current will flow. So, VDD minus IDRD drop will come and this will be as if close to 0, or in other words as if this is output is sorted to 0. So, this is the working principle of NMOS resistive load inverter. Now, suppose this is a resistive load, right, passive load. If I replace this with another MOS, so this will be my pull up network, right. It can pull the logic to the 1 high, and the lower circuit is or lower MOS is my pull down network, it can pull my output to 0, right. And if I can, just like this MOS, this can behave like a switch. If I can use a complementary MOS on the upper side which can also behave like a switch, then I do not need this passive resistor, right. So, we will see this. Okay. Now, when this pull up network is on, suppose pull up network is made up with a PMOS, when this is on, what will be my output? Pulled up to logic 1. Similarly, when my pull down network means NMOS is on, my output will be pulled down to 0. When NMOS is on at logic 1, it should has to be higher than VTH, right. So, logic 1 output is 0. When PMOS is on, when input is 0 and output is pulled up to 1, clear. So, we are getting a inverter operation. So, this is our VTC and this is some important point, that is VIL and VIH, and this is known as our noise margin low and this is known as noise margin high, right. And if we go a straight line at the middle, this is my middle point of this VTC, right. So, what value it will be? VDD by 2, right. If this is 0 and if this is VDD, this value should be at the middle, and this is known as the threshold of the VTC, not VTH. VTH is threshold of the BJT or threshold of the MOSFET, but this VM is known as the middle point or threshold of the VTC. Okay. So, in digital circuit, can you tell me which zone is forbidden? This middle zone is forbidden, because if your input is in between this zone, you are confused, because up to this it will be 0, above this it will be 1. So, if my data fall in this zone, this is my do not care, because you are not sure to treat it as 0 or treat it as 1. Okay. So, the zone which was useful in analog circuit is not useful in digital circuit. So, this is my digital logic, 1 logic, right. This is flat. So, this is output is 1 and this is also flat. So, output is 0, but in between I cannot define, right. If this value is somewhere like this, what should you consider? If some value like this, so it is in gray zone, right. You are not, it is not well defined that which logic to consider, because digital logic is not continuous, it is discrete zone, right. I have a zone which is my 0, I have a zone which is my 1. So, this is my undefined. Okay. So, suppose you have a 0 to 5 volt and you say give 1 volt, you can say okay, still it is 0. You can give 4 volt, you can say okay, still it is 1. But if I tell you okay, this is 2.5 volt, you are not sure. Okay. So, this is forbidden zone. Forbidden means not useful, it cannot decide, right. So, we all know that capacitor has some, this MOSFET has some parasitic capacitance, right. If we think about this node may have some wear capacitance, parasitic wear may behave like a capacitance because they are a dielectric oxide region and so on. So, this drain to body, this capacitance can be there, drain junction to bulk junction, this drain junction to gate junction, another capacitance may be there. Okay. So, all of these capacitance will form a, they will come in parallel and make a load capacitance, clear. Similarly, this MOS when it is on, we are considering some switch resistance, na? It will be in the linear region. In which region it is? It is in linear region, na? When it is on, it is in linear region. So, in linear region it is having some resistance. So, I can model that with R on resistance and C load cap. So, this becomes an RC circuit. Okay. So, RC circuit will deliver some delay, right. Similarly, if my switch is transitioning from 0 to 1, 1 to 0, this capacitor will be charged and discharged. So, some power dissipation will be going on, some power will be dropped as IR heat, right. This resistor will be heated up and some power loss will be happening. So, we can do a calculation for power dissipation. So, the digital circuit or digital logic, we can approximate it as its equivalent resistance and equivalent capacitance to calculate the power dissipations, right. So, what is power dissipation? P is equal to the total supply voltage into total current. So, VDD into ID. Okay. The current flowing through this is say suppose ID. So, power dissipation is VDD into IT. Now, if we want to find the energy, we will integrate this with for a time period 0 to Tc and it will come as VDD into Q. Now, considering this capacitance, we know that Q is equal to C into V, right. As full swing is happening 0 to VDD, so Q is C VDD, right. So, this Q will multiply with VDD. So, total energy is C VDD square, total energy, that is C VDD square. Now, in this VDD total energy, half of the energy will be stored in the capacitor. So, half CV square that will be stored in the capacitor because capacitor is charged up, and another half it will be dissipated as heat, it will be wasted. So, the energy dissipated is half CV square, right. So, from this energy, if we want to calculate the total dynamic power, suppose this logic is functioning at a frequency f, that means the switch is transitioning at T or f frequency, T period or f frequency, that means it is switching on and off, right. So, this if we multiply with this energy, we will get the total dynamic power. The rate at which it is, if it is switching very fast, it will be dissipating more faster. if it is switching very slow, it will be dissipate less, right. Faster frequency, higher frequency, you can check your processor or your mobile phone. Higher frequency means higher power, right, nothing comes at free. If you try to burn higher frequency, you will also have to burn higher power, because it is switching more often, right. So, capacitor will be charged and discharged more often, the resistor will be dissipating heat. So, total dynamic power will be F into CVDD square, right. Energy is equal to power into time, power is equal to this F is inverse, inverse of time. So, if you multiply this energy with F, you will get the total dynamic power. So, my dynamic power depends on which terminologies? It depends on my frequency of operation, it depends on my load capacitance, it depends on my supply voltage. Okay. So, if I want to reduce my power dissipations, which parameters I should try to reduce? Any of this. Okay. So, if you have a higher VDD, you can lower down the VDD. If you have a higher operating frequency, you can lower down the frequency. If you have a bigger MOSFET, bigger size means bigger capacitance, you can reduce down the size. Next is propagation delay. As it is a RC circuit, it will have some delay, right. The signal here, it will take some time to propagate to there. Okay. So, this from the maximum point to the 50% value, this is known as the propagation delay. Okay. So, this is the origin of the input. So, from that time where it is falling up to 50%, this time is known as the Tp high to low. Similarly, on the lower side, the time it takes to reach up to 50% is known as Tp low to high. Okay. So, if I ask you what is the average delay, you can sum them and make a half divided by 2. So, that average delay is your propagation delay. So, propagation delay is your average delay. Now, suppose how fast, if I ask you how fast the frequency can, how fast this input signal can operate, how fast means its time period will be minimum. So, suppose I am taking only this time and this time. So, this will be my T mean. So, in T mean at least I have to give the propagation delay Tp high to low and Tp low to high. If I try to work faster than that, it may not work, but at least this can work. So, the minimum time period is Tp high to low and Tp low to high, roughly twice Tp, and so this is my maximum frequency that the logic can perform. Okay. 1 by T mean is equal to 1 by twice Tp. So, if we discuss about different integrated circuit logic families, so digital IC technologies and logic circuit families, we have CMOS, we have BJTs, we can include BJT and CMOS, that is bi-CMOS, we can have gallium arsenide. Okay. So, in CMOS that presently we are studying, we can have complementary CMOS structure, that is using PMOS and NMOS. We can have pseudo NMOS. Pseudo NMOS means the resistive load NMOS that we have seen. We can have pass transistor logic PTL, and we can have dynamic logic. Okay. These are, most of these are static logic, and there is one dynamic logic. So, you just at this moment you just know the terminology, the details you will learn later. Okay. So, now we are actually studying this and we have already studied this. Now, in bipolar we can have different logic families like the TTL, transistor logic, or ECL, okay, the emitter coupled logic. This is transistor logic TTL, TTL is also very popular, and ECL, emitter coupled logic. And to make it faster we can integrate both CMOS and bipolar, it is bi-CMOS, and this is another newer technology, that is gallium arsenide. Okay. Now, we have discussed like the CMOS. So, this is my CMOS, right. The resistance there we replace with PMOS, okay, and their gate are sorted to input and their drains are sorted to output. See, PMOS source is VDD and NMOS source is ground. So, their drain I have sorted to output. Okay. So, this is my input, this is my output. Now, let us discuss. Suppose input is VDD, source is at VDD, input is also VDD. What is the VGS of this PMOS? 0. So, PMOS will be off. So, if this PMOS VDD side it is off, so as if from VDD side it is disconnected. So, can this output go to VDD? No, it is open. Na? So, now I have given a VDD, this MOS will be on, means as if it is sorted. So, this V0 will be 0. So, this is drawn here, this is open, this is sorted, and this is the ID versus VDS of NMOS. Which MOS is on? NMOS. So, I draw a ID versus VDS is which voltage? V0. Clear? Okay, this is case 1. Case 2, my input is 0. Input is 0 for NMOS. What is the VGS? In gate is 0, source is 0, VGS is 0. So, this is off. So, can this output go to 0? It is disconnected from 0. Can it go to 0? No. Let us see the PMOS. Source is at VDD, gate is at 0. What is the VGS? VDD. So, this PMOS is on and it will pull it to 1. So, let us see this. This is open, this PMOS is short. What is the input? 0. What is the output? Clear, the operation clear? Now, see, if we draw the current of this PMOS, when input is 0, current will be maximum, right, and when input is VDD, current will be, this MOS will be off, current will be 0. So, you see its ID versus VGS is just opposite to that. It was from 0 to this and it is from maximum to 0, because this input is behaving invertedly, right, because in NMOS we are considering VGS, but for PMOS we are considering VSG or mod of VGSP. So, it will be, plot will be just opposite. So, now you tell me, see, when input is 0, this is on, this is off. When input is 1, opposite thing is happening, NMOS is on, PMOS is off. So, both of the NMOS and PMOS are not on at the same time, is not it? When this is on, this is off, when this is off, this is on. So, from VDD to ground, any direct correction exist or not? When this path is on, this path is broken. So, from VDD to ground, you see any current path that is broken. So, my static power is what? 0, right. From VDD to ground no current flows, because when this is on, this is off, and this is on, that is off. So, VDD to ground, in previous case you think this circuit, when this is on, the current will flow through this from VDD to ground. So, some static power dissipation is there, right, but in this case my static power is 0. Okay. So, that is the one of the major advantage of CMOS circuit, that it is so these three are the main advantage of the CMOS circuit, so that modern integrated circuit is made up of CMOS technology. Okay. The static power dissipations in CMOS logic families are 0, because they are complementary in nature. When P is on, N is off, and they have a very high packing density. What is the meaning? That you can integrate more number of MOSFETs, more number of circuits, and its cost of fabrication is comparatively low than the BJT technology. So, BJT technology is more robust, more faster, but costly. Which is better? That will cost more, na? And this technology is little bit difficult to fabricate. So, CMOS has all these advantages. So, present VLSI industry, you will be hearing more about CMOS. All of this present technology, mostly if you check what technology they are mostly CMOS technology. But this CMOS technology is little bit slow compared to BJT. So, we can sometime integrate both of them to make it by CMOS. So, in that platform NMOS will be there, PMOS will be there, and BJT will be also available. Understood the digital logic? So, we are just discussing very briefly. Okay. So, that we already know. Now, can you tell me when input is 0, NMOS will be in off state. When input is VDD, PMOS will be in off state. When they are in middle, both of them will be in saturation. That is where I am using them as analog amplifier, although my range is very narrow, it is very steep, na. So, it is better to use as a digital logic, it is not suitable for analog logic, because your input is so small, even input is little bit more, it will go and clamp. And in this region NMOS is in saturation, PMOS is in linear, and in this region PMOS is in saturation and NMOS is in linear. So, step by step these are the different region of NMOS and PMOS. Quickly, input is less than VT, NMOS is off, PMOS triode region, VT to VIL, PMOS turns, NMOS turns in saturation, PMOS still in triode. In between both of them are in saturation, VIH to VDD minus VT, PMOS in saturation, NMOS enters in triode, because VDS is falling, you see output is falling, and above VDD minus VT to VDD, PMOS goes off, NMOS still in linear region. So, suppose one inverter is driving another inverter. So, this circuit is same, right? This is one inverter, this is another inverter. Now, we told that there will be some capacitive load. Now, who will provide this load? Who will provide these capacitances? There is no physical capacitance. Okay. So, this capacitance will be all parasitic cap or internal cap. That means, the wire will give some cap, the junction will give some cap, right. For example, you see gate to drain, some capacitance will be there, get to drain of the PMOS, get to drain of the NMOS, drain to body of the PMOS, drain to body of the NMOS, and the wear capacitance. So, all of these will be forming this load capacitance. The next stage, this is called the driver and this is called the load stage, right. This driver is driving this. So, this is behaving like a load to this stage, clear. I am having this inverter and it is connected to this inverter. So, this is as if my load to this driver, right. So, its input side, this will also offer me capacitances. So, what is the input? Gate capacitance of the PMOS and gate capacitance of the NMOS. So, all of these capacitance will be summed up and make a equivalent load capacitance. So, we understood that what is the pull up network, what is the pull down network. So, NMOS generally form a pull down network and PMOS generally form a pull up network. Now, in inverter how many input we are having? One input. Suppose I have a NOR gate. How many input I can have? Say 2 input. Say A, B are my input and Y is my output, right. So, what composition I can have? Truth table 0, 0, 0, 1, 1, 0 and right. What is NOR gate? What is OR gate? First tell me. OR means any one is 1, output will be 1. NOR is invert of that. So, whenever there is a 1, output will be 0. So, this is 1 input is 1, so output should be 0, 1 input 1, output should be 0, 2 input are 1, output should be 0, both are 0, it should be 1. So, it is just invert of the. So, let us analyze. Suppose A is 0, this NMOS is off, B is 0, this NMOS is off, any connection to the ground, output can be 0, no. A is 0, this PMOS is on, B is 0, this PMOS is on, output is sorted to VDD, matched, verified, working, okay. First case done. Next case, A is 0, B is 1, A is 0, this path is broken, B is on, this path is sorted to ground, output will be sorted to matching. Let us check on the higher side. A is 0, this is on, B is 1, this is off, this path is disconnected. Can it be connected to 1? No, no, this path is broken. So, this is output is 0, matched. This is parallel, right. So, if I interchange this, still it will be sorted to ground. If both of them are is on, still it is sorted to ground. Easy, no? So, this is my which gate? NOR gate. Similar way, you see in NOR gate, NMOS in parallel, PMOS in series. So, both of them has to be 0 to make it to VDD, both of them has to be 0 to make it to VDD, but they are in parallel. So, any of them 1, still it will be 0. In NAND gate it is just opposite, the PMOS are in parallel, NMOS is in series. Okay. So, this is your task, you should try this. Should we try now? You should answer, okay. 0, 0, tell me what should be the output? This path is totally broken, output is only can go to 1. 0 1, one is off, but other is on, still it will be connected to VDD and this path is still broken. 1 0, same thing, 1 1, this path is now sorted to ground and these two paths are broken. So, it should be, so this is which gate? Okay. That way you can draw any multiple input and any arbitrary gate. Okay. This is another arbitrary gate. So, you can do the all of these are known as the static CMOS logic. So, this type of design is a logic family. Which kind of logic family? CMOS logic family. Advantage, static power is 0 when this pull up network is on, pull down network is off. So, from VDD to ground no direct current flows. So, static power is 0. So, just little bit describe the MOS capacitances. We just describe this now, you see that so many capacitances exist. So, just quickly see what are those capacitances. We know we have a source region, we have a substrate region, right, suppose NMOS. So, this is a P substrate, this is N plus source, N plus drain, right. So, this PN junction will have some junction capacitance, right. Between gate to there is this oxide region that will be provide you some capacitance, that COX capacitance, and this region source and gate you see little bit of overlap is there, right. We told that source region little bit extend in the channel. So, some overlap capacitance will be also formed. Similarly, at the drain side some overlap capacitance will be formed. So, what are the different capacitance? One is gate capacitance, one is depletion capacitance because some depletion layer is forming, and another is PN junction reverse bias junction capacitance. So, you just get familiar with terminologies, you just know, you do not. So, this is the important capacitance we will consider in this model. In previous model we neglected all the capacitance, right, but if you go at higher frequency, this omega, if omega is high, although C values are very negligible, but if omega is high, this omega C will be, you can consider, right, because frequency is now high. Suppose you are going into gigahertz. So, even this capacitance will be now dominant. At low frequency you can neglect them, femtofarad you neglect, but when you are going at higher frequency, this will start to behave, this will reduce your gain, right. So, one is gate to source, this is our gate terminal. So, gate to source one capacitance is there, source to bulk one capacitance is there, gate to drain one capacitance is there, and drain to bulk another capacitance is there. Generally, this source and bulk they are sorted, but sometimes they may not be sorted, right. So, this is known as the high frequency model. The hybrid pi network that we, if you remove this and this and this is your same hybrid parameter, right, same small signal model. Now, why we are considering this CGS, CGD, CDB? Because we neglected those, they exist. When you have a structure, this capacitance by default exist. It is not that we are drawing a capacitance there or we are putting a capacitance there. The physical connections are making up these capacitances. These are internal to the structure. It is not physically there, but the structure will behave like a cap. So, in triode region, you know, our channel is uniform, right. So, our oxide capacitance COX, if we multiply them with W and L, this is my total capacitance. Half of this we will consider at the source side and half of this we will consider at the drain side. Okay. So, that if you sum them, total capacitance is COX WL. So, in triode region CGS and CGD are equal half WL COX. In saturation region what is happening? As if drain is no channel exists, right, drain side it is tapered. So, drain side my CGD is 0 and we are considering that 2/3 of the capacitance is at the CGS. So, 2/3 WL COX is at the CGS. In cutoff no channel exists. So, my CGS and CGD are 0, but gate to bulk that capacitance is total capacitance WLCOX. Okay. My capacitance is WLCOX. In 3 region it is divided into CGS and CGD that way. When it is off, CGS and CGD are 0, but gate to bulk CGB that is equal to like this. Okay. And we know that the source region and drain region they are little bit overlap. So, here I will be having one overlap capacitance, although very small. Why small? Because LD is very small compared to L, LD is very small na. So, this overlap capacitance will be also very small, but still it will be there. So, overlap capacitance is W into L overlap into COX. Typically L overlap is very small. Okay. So, plus this on CGS you have to plus COV, on CGD you have to plus COV, and we have the source region and we have the drain region. So, this is behaving like a tub na. So, this tub will have a bottom plate capacitance, side wall capacitance, all of these are termed as CSB. This is your body na. So, this is CDB and this is your CSB. So, this is known as the junction cap or this depletion layer cap. Okay. This is the formula, you do not need to worry about the formula, you just understand, but this cap value is generally small. If we include them, we will get the high frequency model. So, this is the complete model having all the cap, and if we neglect few cap, this is my simplified model. So, in simplified model what we are considering? CGS, CGD, drain to bulk we are neglecting. So, previously we were having like this gate, that was our low frequency model. Now, gate to source one cap will be there, gate to drain one cap will be there, that is it. MOSFET unity gain frequency. This high frequency model, suppose if we short this output side, if we short this output and try to calculate this short circuit current, then we will get I0 is equal to GM VGS minus S CGD VGS. If we solve this KCL, we will get this. Now, as CGD is very small, we can neglect this term to 0. So, my I is GM VGS, that we already know, right. I is equal to GM VGS, that we already know. One extra term will come due to this. So, if we do this ratio of current, input current and output current, this is known as the short circuit current gain. So, this is GM by S CGS plus CGD, where this is goes to unity, this is known as the unity gain frequency. Okay. So, FT is equal to GM by 2 pi CGS plus CGD. So, how fast your MOS can behave, this will give you that your frequency will fall. So, where it is going to fall at unity, that is our FT, and if FT is higher, that is suitable for high frequency applications, high frequency design. So, this specification is important. This is the definition of FT. Generally this FT varies from 100 megahertz for old technology like 5 micrometer CMOS process to few gigahertz like modern technology like 130 nanometer CMOS technology or 0.13 micrometer CMOS technology. Okay. So, if it is going to high value, it is suitable for high frequency design.